Okay. So, what we said that if the septal coefficient is extracted from male spectrum, then we can get the MFCC. So, how do you do that? Just little bit of detailed discussion how to implement it. So, you know that if I have a SN, I have a signal, speech signal, which is sampled as 16 kilohertz. Okay, a speech signal is sampled as 16 kilohertz. Okay, and then I take a window length, let us 20 millisecond. So, how many samples I should get? 20 millisecond, 320 sample. So, what should be the DFT side? 256. So, n is equal to length of the DFT is 512 point DFT I have applied. So, what is the resolution? 16 divided by n, 16 k kilohertz divided by n. So, I can say 16,000 divided by n is 512, almost I can say 32 hertz, 32 to 33 hertz. Okay. Okay, I am satisfied. The resolution is 32 hertz. So, if I calculate, if I take the DFT n is equal to 512, then I can I get x. Okay. Once I get sk, I can take the mod of sk, which is nothing but a real square plus imaginary square. I can take it. Once I take it, and then I want to plot it. So, this axis is my k axis and this axis is my mod of sk. Okay. Now, if I take it, then what I will do, I will I just sk I have is here. So, what I get, this is the k equal to 0 and then next k equal to 1. So, k equal to 1 means 32 hertz, k equal to 2 means 64 hertz. So, that is why it will going on up to n by 2. Okay. Now, I am calculating I want to implement the male filter. So, based on the male scale, let us design the initial filter bandwidth is 100 hertz. Let us design 100 hertz and center frequency is 50 hertz. So, I can say this is 50 hertz, this is 50 hertz and this is 100 hertz. So, if it is 100 hertz, how many k will be there? So, k equal to 264, k equal to 396 hertz. So, k equal to 3 I can say, almost k equal to 3. So, what is the power? So, k equal to 0 multiply by the filter weight function. So, MLK is the filter weight function. So, if it is this is my first filter I am designing. So, that required k equal to 0 to k equal to 3. So, the value of sk multiply by mk. So, mk means k equal to 0, sk is k equal to 0. Mod of sk I can calculate the mod of sk. So, mod of sk I can get it. So, this capital sk here in this equation in the slide is represent the mod of sk, original spectrum. So, if it is original spectrum, this is nothing but a capital sk I can write down. So, original spectrum is multiplied by the m0. What is the m0 coefficient? Is 0. Then I can find out k equal to 1, then k equal to 2 and then k equal to 3. So, all those 3 will be multiplied by the m function. So, m is called filter weight function. So, that filter weight function multiply by the individual power, then I take the sum, I get the point, this point. Next, I design another filter with 50% overlap. Next, I design another filter. So, that way I can design the filter. So, equation becomes, so Sk is the spectrum, then MLK is the filter weight function multiply and k equal to LL to UL. LL is the k equal to 0 and upper frequency is k equal to 3. Similarly, for the next filter, if it is 50 hertz, is k equal to 2, almost k equal to 2 or k equal to 1. If it is k equal to 1, then k equal to 1 to 1, 2, 3, 4, 5, I can calculate that k. So, you know k ULK or LL is equal to 0 for the first filter and UL is equal to 3 for the first filter. Then second filter I can find out LL may be equal to 1 and I can find out UL equal to 4. That way I can design the filter and find out that S cap L which is male scale spectrum. Then I can take the log of S cap L, because spectral coefficient has to be calculated using homomorphic decomposition which require the log. So, log of SL and then I take the DCT instead of IDFT. Okay. Instead of IDFT I take the DCT. So, complete block diagram MFCC filter MFCC equation. So, this block diagram contain IDFT. IDFT can be easily replaced by DCT, discrete cosine transform. Okay. Why we use DCT? This is the example, this is the reason. The DCT is required to disseminate or differentiate between the or uncorrelated the spectral coefficient, extracted spectral coefficient. So, I use DCT to uncorrelate this filter output. That is why I use DCT, and DCT acts like an FFT. Here I have used DCT because this is a complex. So, the complex arithmetic is required. So, but DCT implementation is easy in this stage. That is why instead of FFT we use DCT. Okay? Discrete cosine transform. Now, I go for the delta spectrum. So, suppose I calculate MFCC coefficient m equal to 1, 2, let us calculate 20 MFCC coefficient M20. So, this is the MFCC coefficient for single frame. I can calculate for next, this is for F1 frame 1, I can calculate for frame 2 M1 M2 dot M20. I can calculate F3 frame 3 M1 M2 dot M20. So, it is said that out of M20 if I take 12 number is sufficient, 12 to 13 number is sufficient. So, instead of 20 I can write M13 I can take, let us I take M13 or 12, let us take 12, 12, 12, 12. Okay. MFCC, if for frame 1, frame 2, frame 3. Now, if you remember, if you see this spectrum of this signal, I can calculate, if you see that I can just show you that spectrogram of a, if you see the spectrogram of this signal, if you see it, look at this cursor, this is the second formant. So, if you see the second formant are moving, even first formant is also moving. So, I can see there is a formant movement, or I can say there is a dynamics of the parameter changing across the segment. So, that dynamics also can be a good features. So, if I want to capture those dynamics, so this is represent the frame 1, this is represent the frame 2, this is represent the frame 3. So, what is the dynamics? Dynamics, difference between the frame 1 and frame 2 and frame 1, and difference between the frame 3 and frame 2 is the dynamics. So, if I say first order dynamics, then I can say F2 minus F1, frame 1 MFCC parameter minus frame 2 MFCC parameter. Okay. So, next F3 minus F2, okay. Then F4 minus F3. So, this is the first order dynamics. First order dynamics. If I want to calculate the second order dynamics, so difference between the first order dynamics is nothing but the second order dynamics. So, first order dynamics is called delta coefficient. So, double delta is nothing but a difference of difference. So, I can say double delta coefficient F3 minus F2 minus F2 plus F1. So, it is nothing but a F3 minus twice F2 plus F1. So, I can calculate the first order differentiation, then I can repeat the same process to get the double delta coefficient where input is this one. Okay. So, delta coefficient is the first order dynamics. So, if I say the formant is moving, so first order dynamics is nothing but a velocity of the formant. If I take the second order dynamics, that is give me the acceleration of the formant. So, how formant are moving? Velocity. How quickly formant are moving? Acceleration. So, delta, double delta can be a speech parameter. Now, if you calculate just differentiate that frame 2 minus frame 1 and frame 3 minus frame 2, suppose you have a signal which is randomly varying, means variation is very high. Let this one, this one, this one, then this one, then this one, then this one, then this one. So, if you see the variation is very random. If I want smooth variation, what I should do? So, instead of taking the just difference between the two consecutive sample, I can take the average difference of few sample, that can be smooth me. So, instead of taking this difference, I will calculate the delta coefficient or the double delta coefficient across the few frame instead of single frame. So, suppose for the first one, instead of taking M1 of frame 2 minus M1 of frame 1, I can say that take few frame M1 and find out the delta coefficient. So, this is the equation. To get the smooth movement of the formant. So, delta coefficient is not just difference between the frame, it is we take several frame and calculate the average difference and then move the filter like a smoothing function. So, that I can get the smooth variation of the formant frequency. Okay. So, that is called delta coefficient, and if I take the delta delta, double delta coefficient. So, now if you remember in the first slides, if I make the MFCC vector features vectors. So, what I said? I take 12 MFCC parameter, then I can take 12 delta parameter, delta MFCC, then I can take 12 double delta MFCC. Now, if you see, if you remember this last discussion, when I put the first filter, I multiply k0th coefficient of the spectrum with the 0, white function is 0. So, I have not taken the energy of the signal. Okay. So, what I do? I will take the energy of the signal which can directly computed after winding. The energy, average energy of the signal I can directly compute, and I take energy, first energy of the signal. Once I take the energy, I can take the delta energy, I can take the double energy. So, that give me 12, 12, 12, 1, 1, 1. So, 36 plus 3, 39 dimensional feature vector. So, MFCC feature vector with a 39 dimension, 39 dimensional feature vector. So, this is called MFCC feature vector. Okay. Next is PLP, very much perceptual PLP, perceptual linear prediction, PLP parameter, PLP, perceptual linear prediction. So, what is that part? Linear prediction, we know LP, linear prediction you know. What is linear prediction you know? So, what is perceptual linear prediction? So, what it is said that if I modify my signal as per the human perception. So, if you see the spectrum of the signal is not at the scale of human perception. So, I modify the spectrum of the signal as per the human perception behavior. Human has a two perception of frequency and perception of loudness. We have not perceived equally loud all frequency, because the LPC coefficient analysis is amplitude dependent, it is time domain analysis. So, across the frequency, if I want to normalize it, so I normalize the frequency parameters with respect to human perception. If you see the block diagram, I am not discussing the detailed slides are there. So, what I said, take the speech signal, find out the first Fourier transform, then calculate the spectrum and modify the spectrum as per the critical band or male frequency spectral spectrum or Bach scale. Then modify the modify the loudness of the, or the amplitude of the spectrum as per the equal loudness curve. Then apply the power law of hearing. What is power law? If you remember that relations between the loudness and intensity, I think it is 445 into I to the power 0.333. So, what it is that? It is the cube root of intensity. So, intensity and loudness relationship is the cube root of intensity. This is constant. This is constant. So, modify the loudness using cube root of intensity. Then take the inverse Fourier transform, or you can say the take the inverse Fourier transform, or then what I will get? I will get the septal coefficient. From the septal coefficient, I can calculate the A1, A2, A3, AP, which I have already discussed. That is called PLP coefficient, perceptual linear prediction. Then there is another speech parameter which is called RASTA, relative spectra. Relative spectra. So, the rate of change of non-linguistic component of a speech and background noise environment often lie outside the typical rate of change of vocal tract shape in. So, it is one kind of modification of spectrum and then find out the parameter. So, RASTA also there is a another side. So, it is a modulate relative spectral amplitude. Modulation filter of spectrum is equivalent to modulation filter of log spectrum. So, those are the modification of the frequency parameter. Okay? So, this is the all about that parameter extraction of the speech signal. Okay? Thank you.